everybody. Good morning from California, and where it is bright and early here. I am amazed that Tushar is awake because he is either on India time or on California time, which means that he never sleeps, basically, between the two. I'm going to give a talk on SATCOM arrays, and Jen Baines referred, basically in his talk, he talked a little bit about the future SATCOM, and maybe we should not call it future anymore. It is here, and how we are building them, and how we are going to build the next generation of them. I'm a professor at the University of California, San Diego, and maybe without doubt one of the prettiest and nicest places in the world. So do come and visit us if you wish. So we'll talk a little bit about LEO SATCOM, and then we will talk about silicon and some other technologies to the rescue to make it low cost. We will talk about some Ku band phase arrays and Ka band phase arrays, and then we will talk about the future, which is a Ku, Ka combined, and a bit of a conclusion. So in the old days, that means, up to about a few years ago, we basically built satellites at the GEO orbit. GEO means geostationary orbit, and it is at 36,000 kilometers. And it's actually kind of not discovered, proposed by Arthur C. Clarke, who was a professor at Cornell. And in a sense, as the Earth rotates, the satellite rotates at the same rate. So if you are on Earth and you are looking at the satellite is always exactly on top of you. However, it's very far away, and therefore these satellites need very large antennas because you are communicating at 36,000 kilometers away, and require very large power, and they become very expensive in the hundreds of millions of dollars. And since they are very expensive, you basically have to design them to last 10 to 15 years. Then we said, okay, this is good. And this is how we did satellites from the 1970 till the 2000, maybe 16, 17, which is, 45 years. Then we said, okay, let's not do that. Let us now put communication satellites in LEO, low Earth orbit, or MEO, middle Earth orbit. Now, middle Earth orbit, MEO, there is only one company, SES, who has there, which is, let's say 5,000 kilometers to 10,000 kilometers in the middle. But LEO, this is where Starlink, SpaceX, Amazon Kuiper, and everybody is there. Now, the satellite is very close to Earth and pulled by the gravity of the Earth. And when you pull somebody by the gravity of the Earth, because of the centrifugal force, they have to turn. And they turn much, much quicker than the Earth's rotation. And therefore, the satellite, if you are over ground, is zooming, literally zooming. And it typically will be above you only for about 5 to 10 minutes. Really, 5 to 10 minutes. And you always have to track it. You always have to have an antenna that is moving and tracking the satellite. And pretty fast, from the time you get it at the horizon, your horizon, until it goes above you and then it continues down, the whole thing is about 5 minutes or less, depending on the orbit of the satellite. So therefore, now you need an antenna that is actually scanning the beam all the time for years and years as they are tracking satellites. Now, who is doing it? Well, clearly Starlink decided, and they started the massive constellation. They now have 6,500 satellites in LEO. OneWeb has about 900 satellites in LEO. Telesat tried, they failed the first time. They only launched a couple of satellites, and now they are trying again with about 400 or 500 satellites. And Amazon Kuiper wants to be as big as Starlink and wants to launch 6,000 to 10,000 satellites. Now, they are not the only ones. The European with IRIS-2 is launching 300 satellites. Taiwan announced this year they want to launch 300 satellites. Korea announced they're going to launch 300 satellites. China has announced they want to be as big as Starlink and Amazon and launch 6,000 to 10,000 satellites. So, and India will be announcing soon. So basically the whole world can do that. So we basically need a phased array. And what does a phased array mean? A phased array is, as you will see, I will show you, is an antenna like this one on the front of a plane, or this one on top of a plane, or this is a Navy one, a Navy radar, is an antenna that has phase shifters and that has gain control on every element. And it could be made out of thousands of elements. And where by changing the phase shift and by changing the gain on each element, mostly the phase shift, you basically can steer the beam, can point the beam there to the left, to the right, plus minus 30, plus minus 45. You can steer the beam at any angle. And you do it electronically, and it happens in tens of microseconds, whatever it takes to change a phase shifter, basically. And you need a lot of elements, as you will see in the slides. You add them all together, and then you put your transceiver, transmitter receiver. This is the block diagram is shown in the receive side, but really there will be one transmit and one receive. Now, the concept of the phase shifter, as we will talk about, where do you put it? This is called RF beamforming because you put the phase shifter in the RF path. However, you can mix down and put the phase shifter in the IF path. So you could see here the phase shift. You first mix down to an IF. Rather than working at an RF of 20 gigahertz, where, for example, Amazon Kuiper is, I first mix down to L band to 1 or 2 gigahertz and put a phase shifter in the IF band. Or you could say, I am going to put a phase shifter in the LO side, like it is here. And therefore, when I shift the LO in phase, I'm shifting the IF in phase. Or you could say, I don't want any phase shift. I would just mix, sample with an ADC, and turn all my data, all my signal into ones and zeros, and then do all the beam computation using an FPGA and DSP. Well, after 10, 15 years of research, this is dead, no one uses it, and this is dead, no one uses it. On the ground, we all use RF phase shifting, and on the satellite, we all use digital beamforming. We use RF phase shifting because it's the easiest. It does not require mixers. Mixers require a lot of power and generate a lot of spurs and are not very linear. So just because of power and spur issue, we all are now using RF phase shifters on the ground, and we are using digital beamforming because digital beamforming, yes, the mixer does consume a lot of power, and yes, you have to make it very linear, but in DSP, you can make hundreds of beams in different directions at the same time. So we know how to build phase shifters. We know how to build everything. This is a gallium arsenide chip, which contains 2 channels, built by Lockheed Martin and by Boeing, published long time ago, 2007. It's going to be nearly 20 years ago, with its silicon controller. This is a Marconi radar TR modules. You could see the PA, you can see the circulator, you can see the LNAs, and this is the phase shifter chip, and this is the VGA chip. So we know how to do that, but they are expensive because they were built on gallium arsenide. We have put them on planes, on top of planes, we have put them in head of plane, at the front of planes, and we have put them on huge Navy radars. And look how many elements. There are thousands and thousands of elements. And I can tell you there are thousands of elements here, and there are thousands of elements here too. So 22 years ago, when I was a student, when I was a young faculty, and working at Boeing, we basically said, you know what, silicon is coming, and let us replace all the phase shift and the amplitude control and everything using silicon function. And let's leave the LNA in gallium arsenide or the PA in gallium arsenide. Today, even the LNA and the PA are now all in silicon. And we proposed this to Boeing in 2001. And Boeing loved it, and DARPA loved it, and they started funding us. And we were pretty soon building silicon chips that have 8 channels, 1, 2, 3, 4, with a Wilkinson here and generating all the functionalities of 16 to 32 gallium arsenide chips, all in a single silicon chip. So you can see the immense reduction in cost. Same thing, we can do transmit receive chips. This is transmit receive, and this was used for radar or half duplex or TDD-COM, and led to 5G at millimeter waves. So typically what you would do is that you would take your antennas and you would put the silicon chip here, and then you, which has, as we say in the transmit, for example, 8 channels, because you want VH, 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 you want dual polarization. On the receive, you can even put 16 channels in order to have multiple beams, because after you receive, you can break it into channel 1 to point in theta 1 and channel 2 to point in theta 2. And you will have 2 Wilkinsons, and out you go. And then you put these chips on a large PCB, and you grow as large as you want. They could be receive only, they could be transmit only, they could be transmit receive. Now, one thing that you realize is that, okay, I need to put them on a PCB. And if I put them on a PCB, I need the PCB to be able to handle hundreds of chips, if not thousands of chips. So the PCB technology became very, very good. And this has nothing to do with satellites. The server people and the base station people demanded very large PCBs. The packaging, which now we do QFN and BGA, has become very good. The CG and CMOS became very good, and the planar antenna technology also became very good. So we put all these 4 technologies together, and you will have chips on one side, antennas on the other. And then in 2010, 14 years ago, we were sending our chips from UCSD to Rockwell Collins, putting chips on one side, antennas on the other side, and we were steering the beam. That's a beam that's at broadside, and that's a beam steered to 45 degrees. So really, what do you need? You need teamwork. You need a group that does the RFICs, or you can go buy them from Renaissance and others. You need a group that does the antenna and EM design. You need a group that does thermal. You need a group that does the packaging or the PCB design. You need a group, which is the PCB design. You need a group that does the power and SPI control and Ethernet and so on. And you have to put them all together in order to make a phased array. And that's basically how you would do a cell phone or a computer or a radio transceiver head. You need many, many groups with different backgrounds in order to put it all together. So by 2014, we were building with Rockwell Collins, like only a few years after we started, we were building with Rockwell Collins huge phase arrays, 2,400 elements, with 2 simultaneous beams and 1,400 elements. And Ball Aerospace followed us, and then Boeing, released their own arrays at Ka band, which are on the MQ-25. And that is transmit and receive. And you will see how they are built. But there is no one who took this technology better than and used it to its advantage better than SpaceX. Look at this PCB. And look at the number of chips. These are all analog beam forming chips, all of them. And you could see here the Wilkinsons and the transmission lines and everything. And then this is the power supply. Clearly, these are the power supply here. And this is the clock here. And this is later on for the modem. And one chip is the processor and the modem and so on. And they made Starlink phase arrays. Today, they build 20 to 30,000 phase arrays a week. They have, all the chips are built at ST. Actually, when you look at them, there is an ST mark on them. And they have, I think they are now at 30,000 phase arrays a week, 1.5 billion transmit receive channels. Every phase array contains 1,000 elements. And they are selling it to you at $500. That's 50 cents a phase array channel. Transmit receive phase array channel. But as I said, there is many more coming. Amazon has shown this year and announced their terminals, and they will start most probably, and this is a mistake, in fall 2025. They're gonna start launch in fall 2024, and the service will start next fall in 2025. Hughes has made terminals for OneWeb. Intellian is trying to make terminals, and now you have many, many, many companies making terminals. And these are the Starlink satellites, where each one of them is about 4,000 element arrays, approximately 4,000 to 5,000. Each one is digital beamforming. Digital beamforming, that means each one of them has a mixer and ADC at the element. And each one of them can make hundreds and hundreds of beams. That's unbelievable. Now, well, you know what's unbelievable about it is that Amazon will build, I mean, not Amazon, Starlink will build 4 satellites a day. They build in a week now more than the entire world builds satellites. Can you imagine that? They build, you know, 30, I mean, I'm sorry, maybe they build in a month now more than the entire world builds a satellite. They will build in a week more than like entire Europe or all other US companies build satellites in a year. It's unbelievable what they can do. And these are the phased arrays at KU band. So the winners in satellite today is definitely ST Micro, ADI, and Renaissance. ST Micro is with Starlink. ADI does a lot of chips for the satellite side, and Renaissance is the largest winner on the ground terminal side. And the processes that they use, the silicon processes, can either be Global Foundries or ST or TowerSim. Now let's talk about the Renaissance chips. As I said, you can make chips that are transmit, which are 8 channels, or receive, which can have 8 channels or even 16 channels. And Renaissance leads in this, worldwide leads. There is no one that comes close to them. There are other companies that do it, but there is nothing, no one that comes close to Renaissance. And most important is that their LNAs can have up to 1.3 dB noise figure using silicon, not gallium arsenide, using silicon at 20 gigahertz, which is amazing. And it used to be that their LNAs were 1.5 and 1.9, but now they release new LNAs that are 1.3 dB noise figure. And here they are. These are measured LNAs. You cannot even do this in gallium arsenide, where you could look at this. At 9 milliwatts, you have 1.1 to 1.2 dB noise figure. And at 15 milliwatts, and 24 dB gain, and at 15 milliwatts, and 24 dB gain, you have 1.3 dB noise figure now, gallium arsenide might give you an LNA with maybe 1 dB noise figure, but it will cost 50 times more, 10 times more. These are extremely low cost, and the power is very, very low. And to add that they have the beamformer chips. So the phase shifters are phenomenal. Phenomenal. These are the 64 phase shifts, and look at them going like this, 64 phase shifts. RMS errors of 2 degrees, this is ideal. They are perfect. RMS gain error 0.2 dB, again, perfect. So let us see how we build a KU band SATCOM array. We have a company called Extreme Waves. This is a 1024 element. Of course, it can grow as large as you want. And it is a PCB on one side and the chips on the other side, very much like we show. And these are the measured patterns. And this is, and it has all based on the Renaissance chips. And this is, you could see how the measured patterns are nearly perfect. And this is at 11 and 12. These are the KU band. And this is for beam 1, and this is for beam 2. Look at that, beam 1, beam 2. It's perfect arrays. And the G over T is 11 dB over Kelvin, which is nearly as good as a 30 centimeter dish reflector. Amazing. Amazing that now you have a piece of PCB that has that. Now, at KA band, again, you see the PCB. This is the PCB. The chips are on the back. The PCB is in front. Now we are talking 30 gigahertz, not 12 gigahertz, 30 gigahertz. And typically, that's the radon. These are the fans. And this is a typical box. They do consume power because the EIRP is very large in a very small space, 48 dB watts. 48 dB watts, like 150 dB watts will be 100 kilowatts EIRP. And again, these are the measured patterns and scanning to 75 degrees. This is a 1024 and this is an 880 as an example. You could see the side lobes. And this is the EIRP again, 78 dBm, which is 48 dB watts. Yeah. Now, what is most important is the actual ratio, which would be the cross pole. You could, because the chips are so perfect and everything is done on a PCB and there is no hand tuning, then look at this. When it is calibrated at 0 degrees, and then we go measure the actual ratio and the cross pole, look at this, how it remains less than 1 dB, which is 25 dB cross pole, all the way to 60 degrees without further calibration. Again here, when we calibrate at 29.5, you could see how it remains from 27.5 all the way to 30.5, again, less than 1 dB. So it's because everything is done automated, precisely, the chips are nearly perfect, and only a 1-point calibration, and you are done. This is a SATCOM receive, again, a PCB, and then and it has at 20 gigahertz, 17.7 to 20. And then you could see the 2 simultaneous beams and 2 simultaneous beams and a G over T of 10 dB over Kelvin. So basically, by just doing chips and PCBs and commercial chips from Renaissance, we basically have been able to make phenomenal phase arrays. Now, where is the future? Well, the future is that we make everything wideband. Rather than have a narrow band at KU and a narrow band at KA, we make channels that are all wideband. And we make a wideband transmit phase array, and we make a wideband receive phase arrays with 2 beams. So we went and we built these wideband arrays, wideband transmits. So this is 8-channel chip, and here it is with the bumps, and it is flipped. And we connectorize it. And you can see that today in silicon, which is amazing, we can make silicon chips that go from 5 to 33 gigahertz. Each channel has 6-bit amplitude and phase control. And that can do X-band SATCOM, C-band SATCOM, X-band SATCOM, KU-band SATCOM, and KA-band SATCOM, all at the same time. On the receive, again, it has 2 channels, and this one is from 3 to 28, and KA-band SATCOM is 20 gigahertz receive, 30 gigahertz transmit, so you really don't need to go more than 22, 23. And again, you can do C-band and X-band and KU-band and KA-band, all from the receive. Look at the noise figure. This is such a wideband chip with 16 channels, and it has a noise figure of less than 2.3 dB from 3 to 21 gigahertz, which is amazing in silicon. And again, you can see the phase shift, and you can see the RMS error, and it has 16 channels allowing you to have 2 beams. So the future is now we are working on KU and KA band and X-band, XKU, KA band SATCOM, all from the same aperture, so that we can replace 3 dishes and 3 systems and have 1 system that does all of them together. So to conclude is that because of silicon and because of PCB technologies, we have cracked the puzzle, and now we can build affordable phase arrays at any frequency, any bandwidth, and in any form. As you have seen from Starlink, and you will see from OneWeb, and I mean OneWeb is there, and Kuiper, these phase arrays are built in the tens of thousands per week. Tens of thousands per week. And they are being developed at a very fast pace, both on the ground and on the satellites. The RFICs have been essential. The silicon RFICs have been essential, and without doubt, on-the-ground terminal renaissance leads. Now, I make it look easy, but packing 1,000 channels or 2,000 channels on a single PCB without oscillations requires hundreds of thousands of vias for isolation. So we have 16 to 20 layer boards with a lot of isolation between inputs and outputs and filters and this and that in order to make it happen. And in my opinion, without doubt, that silicon and silicon RFICs and planar low-cost phase arrays have changed the world, and they have allowed LEO SATCOM to happen. And my motto is that anything that can be done with phase arrays will be done with phase arrays, because no one wants to use a big mechanical steered reflector, and everybody would like to use an electronic scan phase array. And thank you. That's my talk.